This is one of a series of lectures produced by the Further Mathematics Support Programme for A-Level Mathematics Revision. In this lecture we're looking at the Edexcel Decision Mathematics 2 specification, and the topic is transportation problems. The specification says that you should use the northwest corner method for finding an initial basic feasible solution, and having found that solution, use the stepping stone method for obtaining an improved solution, and that will include calculating what are called improvement indices. It says the problems will be restricted to a maximum of 4 sources and 4 destinations, but the idea of dummy locations and degeneracy are required. So I'll try and explain some of those terms before going on and looking at an exam question. The form of the information we're given will look something like the table below, where we have 4 supplies or sources, 1, 2, 3 and 4, and in this case 3 demands, A, B and C. The actual values of the possible supply from each of the sources is across at the right hand column, so the 20, 30, 20 and 10, and the demands that we're trying to satisfy for each of the destinations in the final row. Now in this case you'll see that the total supply that's available is actually 80 units, whereas the demand currently is only 60. So we have a situation where the supply is greater than the demand, and this is where the need for a dummy location comes in. So what we're saying here is, let's add in another location which is known as the dummy, which has a demand requirement of 20 units. That then balances up the supply and demand so that they're equal to each other. So this is our idea of a dummy location. The center part of the table shows the costs of moving units around from the source to the destination. Initially we don't get involved with the costs, we simply want to know, can we satisfy the demands from each of the supply points? And that's where the northwest corner method comes in. We start literally at the northwest corner of the table, so the top left hand side, and look at the supply from source 1. It's equal to 20, and there's a demand at A of 10, so we can fully satisfy the demand from that supply, leaving an extra 10 units which can be used for supplying some of the demand of B. So we then keep moving down towards the bottom corner in this sort of fashion. B requires 15 units, so we can get the extra 5 required by using source 2, but there's a total of 30 there, so there are 25 left over to satisfy some of the demand of C. That leaves 10 to follow on, and of source 3 then 10 units are available for the dummy, and finally the 10 units that are currently in source 4 will also go to the dummy. The number of cells that we've used should always be 1 less than the sum of the rows and columns. So here we've got 4 rows and 4 columns, and we've used 7 cells. However, it is possible that that doesn't happen. So for example, in this table here, let's say that we fully satisfy A as demand from source 1, but it uses everything up. So when it comes to B, we then move down to this position using source 2, and then we continue in the sort of pattern that we've looked at already. And now you see we've actually only used 1, 2, 3, 4, 5, 6 cells, and that's because of this diagonal move. At this point we didn't go to this cell here. So what we do in those situations, this is what's called degeneracy, and we arbitrarily put in a value of 0 so that we always have m plus n minus 1 cells. In this case, 4 plus 4 minus 1 is 7. And that 0 can be placed in either of the squares to avoid that diagonal move. The next step is to turn our attention to the costs involved, and this involves looking at the cells which have got numbers in them, so the ones that we've got in the table there, and then looking at the costs in the initial table which showed how much it takes to transport units from source to demand. We start off in the top corner again, putting what's called a source cost. These are called shadow costs. So we have one which is the source 1, which we set at 0. And then from using that we can find values for the destination of A and for B by using these two cells, the costs associated with these two cells. And so on, we move through the table working out the shadow costs for each of these positions in turn and the demands for C and D. That will become clear when we do a full-blown exam question in a second. From the shadow costs, we can then calculate for the uncovered, or the cells without values in them, what are called the improvement indices. These are the things which show us whether we're going to be better moving something via a different route than we're already using. If an improvement index is negative, it indicates that we can improve the costs associated with the supply and demand routes. And so we choose the most negative one. Let's say it was 1D in this particular case. And we then say, well, we're going to choose to move some units via that route. We normally call it theta. Then by what's called the stepping stone method, we decide how many we can move via this particular route, and that goes by stepping around those elements in that pattern of crosses that we have on our table. So we'd have to come to this one, this one, this one, this one, this one, and then finally back. This is the stepping stone that's going on, and at each case we'll be able to decide then what changes to make in the supply and demand, and hence calculate the new savings. Now that's the general method, and of course it will become much clearer when we look at a specific example, which I'm going to do now. Okay, here's a question from June 2011 then, and it's, as you'll see, it says the table shows the cost of transporting 1 unit of stock from each of the 4 supply points to each of the 3 demand points. It also shows the stock held at each supply point and the stock required at the demand point. So just as the table I've been talking about. And we're looking to try and find a minimal cost solution to this problem. The first thing we have to do is to add a dummy demand point and appropriate values to the table in the answer booklet. So that's the idea that we actually have at the moment something which is unbalanced. So supply and demand are not equal to each other. We're given an initial solution, so we're not going to use the northwest corner that I've already described before. This has been done for us, and this is our initial solution, which would have been developed by the northwest corner method. And what we want to do then is to calculate the improvement indices, some of which have already been done. So in part B, we're going to use the shadow costs, calculate, and then to then use those to find the missing improvement indices from the table. Then finally it says taking the most negative improvement index to make changes using what's called the entering square and using the stepping stone method. So that's that final part of the solution that I was talking about a little bit earlier. So in the first part of the question we simply need to balance the supply and demand. So the dummy will have costs of 0 associated with it. Nothing's actually going to move, so it's not going to cost anything, but it will need to have an extra demand. So what we need to check is look at the supply. At the moment we've got a total supply of 100, but the demand is only equal to 90, so we're going to have an extra dummy demand of 10 units. That's all that's required in that first part, showing how you would use the dummy. In the next part of the question you can see actually that the northwest corner method has been used, so we're not actually being asked to do it, but however you could check through yourselves and see that that is the solution that you would get by using that northwest corner method. What we are going to do now though, however, is to calculate the shadow costs and then what are called the improvement indices. We start off then at the top corner again. This is source 1, and we allocate that a shadow cost of 0, arbitrarily give that 0, and then we're going to from that calculate the demands and source costs of each of the different locations. We do that by looking at the cost table that we've got, and we can see that there's a total cost of 31 in moving something from 1 to A. So if we've said that the source value is equal to 0, then the demand of A must therefore be equal to 31. But if that is equal to 31, we can see that the total cost from going from 2 to A is 22. So we therefore have a shadow cost for source 2 of -9. Now don't worry about the fact that that's a negative value in this cost, because all we're doing is we're working out relative costs involved, and we're seeing if we can make improvements. So the -9 is quite okay. From the -9 we've got to move across to the next cell. Remember, we're looking at the costs associated, and here we've got a value of 33. So 33 means that the demand at B, the demand cost at B must be equal to 42. We keep doing that in exactly the same way, moving down to the next cell. Here we've got 42. We need a value of 27. Which means that 3 must be equal to -15. Moving along, if that's -15 at C, we need 32, which gives a value for the demand of C of 47. And then coming down to the 38 in the cost table means that we have a source cost for 4 equal to -9, and finally that means because we've got a cost associated with the final cell of 0, because it's the dummy, remember, then we're putting in a demand cost there of 9. We now calculate what are called the improvement indices, and some of them have been done for us. So to show you what's happened, let's take the improvement index that has gone in for 1B. The cost moving from 1 to B is 29. So we take that value, 29, and subtract from it the source cost for 1, which is 0, and the demand cost for B, which is 42. And that gives us a value of -13. which is what has been put in the table for us. So we've now got to look at some other values. You see that it's the cells which don't have the X's in them, because that's the pattern of our supply and demand. The X's have gone in the positions that I'm indicating on the cost table at the moment. So we're looking at the other costs. So we need to look at the improvement index for 1C. Well, the cost associated with 1C is equal to 32. The supply is again 0, so the supply for 1 is 0, and the demand for C is 47. So we're taking 32 minus 0 minus 47, which gives us negative 15. So we're writing in here negative 15. In a similar way, we can calculate the others, which I will do and move forward. So there we are, all complete now, and you'll see that the other values came out to be 9, 0 and 6. Some of these improvement indices are negative, and so we can make improvements by changing the supply to one of those. The most negative of those values is the negative 15 that we found in 1C. So we call that the entering cell. So 1C is the entering cell. And what we're going to do is to put some of the supply and demand along that route from 1 to C. We don't know how much at the moment, but we're going to call it some value. Let's call it theta. Now, following the pattern of X's, we're going to step round our table, getting back to that position. So let me show you that happening in the pattern of X's that we've got. And see how we can do that. So from from 1C we can go to 1A, then down to 2A, then to 2B, then to 3B, 3C, and back up to C. Notice we don't use the other two X's. So this is our pattern. This is what's called the stepping stone, and we're going to follow this pattern round the table. So what we're going to do now is follow that pattern, looking at the current supply chain. And it says if we're going to supply theta via the route 1C, well, from 1 we've already got 20 going, so that means we're going to have to change that to 20 minus theta. But if we change that, it means we're going to have to add 15. It's going to have theta added to it, plus theta. But that means that the element in 2b, which is 7, is going to have theta subtracted from it, because the total supply and demands are going to have to be the same. So then moving down, we're going to have to add theta to the 18, which is in that cell, and finally subtract theta from this one, which has got 2 in it. So that process doesn't actually doesn't actually change the total supply and demand. It simply changes where they're coming from. And what we need to do is to look at what's the most change that we can make. Well, because this is 2 minus theta, and we look at the negative ones, the other one was 7 minus theta and 20 minus theta. This is the most we can change things by. So theta will be equal to 2. And that will be 0, so it's this cell, 3C, which is our exiting cell. Well, the final part of the process is then to make that change, so we put 2 into cell 1C, which means that this becomes 18, this one becomes 17, this becomes 5, the next one 20, That will be 0. This becomes 28, and we've still got 10. So you'll see that we've still got 1, 2, 3, 4, 5, 6, 7 cells. Well, that's as far as we've been asked to go in this particular question. However, it could be that you have to repeat the whole of the operation over again. So we could find the shadow costs associated with this new table, the improvement indices for the vacant squares at the moment, to see whether we can make even further improvements. However, as I say, that's as far as we need to go with this particular question. It was to go through and just do the improvement method only once. Let's look at the marking and how that was done for this question. For the initial putting in the dummy column, including the 10 at the bottom, there was a single B mark. In calculating the shadow costs, then there was a method mark for getting, I think it's 4 of them correct, and then if you got them all correct, so it's a correct answer only, CAO mark was it for the accuracy. The indices, the improvement indices, again a method mark as long as you've got 3 correct in this case, and then an accuracy mark, which was again was CAO, so correct answer only. Filling those in on the table didn't produce any extra marks. It's just a case of producing the values and putting them in there. In doing the stepping stone method, there was a method mark and again an accuracy mark given for those. And for stating the accuracy mark was for stating the entering and exiting cells along with the value of 2. And then finally, as long as everything had gone correct up to there, there was another dependent method mark, a D mark, which means that that's dependent on the method so far being correct, and an A mark, and again CAO, correct answer only. The final part of the specification says that you may expect to produce a linear programming problem from a given transportation question. So just to look at that idea, all you need to do here is to first of all define the variables, and in this case the variables we would define as being x, I, j, and we say that is where this is the number of units transported from I, so transported from I to j. We could say row I to column j. And that's a variable. So I depends on is part of the set ABC, and j is in the set RST. Sorry, that symbol there should be an element of rather than equals to. There are non-negativity constraints which we're used to, so x, I and j, or x, I, j are all greater than or equal to 0. We want to minimize the cost, so that we minimize the cost. Well, the cost can be calculated by simply taking 3 times x11, which is the cost associated with the x11, plus 3 times x12 plus 2 times x13, and so on through the table. So we're just simply putting in the cost variables, sorry, the cost amounts from the table associated with the x variable, xij variable. So I'll finish that off and come back to you in a second. And there we are, complete. And you see, if you do it in that form, that all you're doing is literally taking those values from the table and putting them in front of their variables. There are constraints associated with this. Well, the constraints are simply statements of the possible supplies, so that the amount we supply from A has got to be less than or equal to 25, from B less than or equal to 40, and from C less than or equal to 31. So that is a case of saying that the supply from A, which is x11 plus x12 plus x13, is less than or equal to 25. And similarly there you can see that I've put in the constraints for the supplies from B and C. Well, those were the supply constraints, and in a similar way we can look at the demand constraints. So the demands are looking at this time the columns, so that we have 3 which is x11 plus 4 x21 and 3 x31, that's less than or equal to 30. So that's the demand for R. Sorry, what I've put in there is actually the cost, isn't it? And it shouldn't include the cost variable at all. The cost amount is just the variables, the actual demand. So it should just be x11, x21 and x31. And then if we move along to S, for S it's the second column, so it's x12 plus x22 plus x32. And that's the demand for S, and that's also less than or equal to 30. And finally, the demand for T is the third column, x13 plus x23 plus x33, and that's the third column, and those are less than or equal to 36. So these are the demand constraints. So quite a lot of writing down of algebraic equations there, but if you remember that we have got, once you've defined your variable correctly, the non-negativity constraints, but then minimizing, so this is our objective function, and then a list of constraints. I wouldn't normally write it up by the table like that. I'd put the constraints together, but it's just to show you where they were coming from, that first point. So they're the supply constraints and the demand constraints, together with the non-negativity ones. So that shows the general principle involved then in doing a linear programming question, setting it up for linear programming solution. Well, that's the end of the lecture on transportation problems. The other modules and topics can be found on www.furthermaths.org.uk.